Swayam Prabha. Digital India. Educated India.
Welcome back to the second part of arrangements. So to quickly refresh and recap, what we did in the first part was essentially showing the relationship between points and lines using a transformation called dual transform, so that the problems involving points are not very different from points problems involving lines. So lines and points are two faces of the same coin, kind of, that was the objective of the first part of the lecture. Now let me take it further. So now let me get more into arrangement. So rather than looking at problems involving points, which we know that we can now map into lines, let's explore that structure. Okay. So that structure is essentially the lines. Okay. So so I said here is a set of lines L, L1, L2, L sub n. Okay. And let's study what is the structure these lines actually impose on the plane. And I'll stick to lines on planes, because drawing planes on 3 dimensions is not possible in the screen, and it doesn't convey the essence as easily as I can do using 2 dimensions. But all these have a very natural analog in the higher dimension. In the higher dimensions, we are talking about planes or hyperplanes in some d dimensions. So the first thing to note about such a structure is, okay, let me just label them first. So there are only 4 lines I have drawn. Okay, 4 lines. So I have these 4 lines. Of course, in general there are many more lines. So what is the let us say the partitioning that it imposes on the plane? Okay. So the when you look at such a structure, okay, and you see essentially the lines are like you can define a graph basically on this. So this is, let us say, A's of L is this. I am formally now introducing arrangement of lines. Okay, this is a structure that is called the arrangement. And what do we mean by arrangement? The arrangement essentially means that we define the structure that is induced on the plane. Okay, what is the structure induced by L? That's basically the arrangement. Okay. And what comes across very readily is it's a graph basically that is getting defined. Okay. And the graph is defined by the intersection points can be thought of as vertices. Okay. So these are precisely the vertices. Okay. And as I said, if we assume that the arrangement is a simple arrangement, so in a simple arrangement, no 3 lines are concurrent. The number of intersections is given by n choose 2, right. Every pair of line intersects in a point, and that is basically going to be our set of vertices. Okay. So, V basically corresponds to this intersection points. Right. Now, clearly the edges will be basically the part of the line joining to consecutive intersection points. So, then basically this is an edge, this is an edge, this is an edge. Unfortunately, how about this? So, because there is no more intersection points, okay, it does not quite fit into this definition. So, what we will do is we can make some assumption, not a kind of a convention that these infinite rays, okay, which are can be. So, it is not an edge in the sense that it is not bounded by vertices on both sides. We can imagine that there is a vertex, we can think about. So, this is a kind of a planar graph. Let me first actually point out what is this planar graph. So, this is E, okay. Let me just leave this and I will come back to it, what happens to these semi-infinite edges, okay. So, there are some semi-infinite edges, right. So, we will deal with the semi-infinite edges. So, that we will deal with. Before that, let me mention what the faces are, right. So, the faces again. So, it is a planar graph, right. So, now this is a face. Is this visible? Okay. So, that is a face, this is a face, this is a face, and now when it comes to some of these faces again, these are not bounded faces, right, because the same reason that the edges are semi-infinite, these faces are unbounded, right. But still let us live with that, okay, and let us see how to deal with it. Okay. So, the faces bounded plus unbounded defined by a cycle, right. So, this is clearly there is a cycle defining this cycle of vertices, this is a cycle. Unfortunately, this is not a closed cycle, right. So, this is open, basically these are unbounded, these are unbounded. So, one thing we can imagine is that suppose I put this graph on a surface of a sphere, okay. Instead of drawing it on the plane, suppose I put it in a sphere, then all these semi-infinite edges we can take it to some one point on the other side and make them join, okay. It still remains planar, right, and once it remains planar, we can apply many properties of the planar graph, that is the reason, okay. So, imagine a point at infinity, or let us say embed on a sphere, let us say some special point capital, no, let us not use capital P, let us say some capital Q, okay, such that all semi infinite edges converge in P Q, then that implies all faces are also bounded. Right. So, this is the structure basically induced by a set of n lines. And now since it is a planar graph, okay, as I said, you can apply all the properties of planar graph on this. And the first thing that comes to mind is how many faces and how many edges. We know the number of vertices is equal to n choose 2 in a simple arrangement. Okay. Now, how would you count the number of edges on the structure? How many edges are there? So, there is one thing that you can easily invoke, I mean without even blinking, and that is because it is a planar graph, okay, from Euler's formula, the number of faces, number of edges, number of vertices are all sort of linearly related to each other. So, once I have got a bound on the number of vertices, okay, that is about n square, right, this is about n square, let us say n square by 2 or whatever. Then the number of faces, number of edges will also be bounded by this. Okay. That is one way of sort of just brushing it aside. On the other hand, you can actually look at it more closely because it's a geometric graph, okay, sorry, defined by some geometric objects. And let us look at one line, any one line basically like this line. So, this line basically will contain how many intersections? N minus 1, right. So, there are n minus 1 intersections and therefore, there are how many edges? Well, including the 2 semi-infinite ones, there will be n edges, right. So, each line basically contains n edges and therefore, the n lines will contain about n square edges. So, you got a bound there very easily. Right. Similarly, you can argue about the number of faces. One is that you can plug in the Euler's formula. Okay. So, I think we can plug in. So, one I can do that. I have the number of edges, I have the number of vertices and I use this. So, if I am not wrong, it is V minus E plus F equal to 2, right. That is your Euler's formula, right. So, let me just quickly check minus 1 plus 1, yeah, right. So, I can just plug it into this formula and get the number of faces out of it. On the other hand, I can also do some kind of geometric arguments. So, if you look at any intersection point, okay, every intersection point basically defines a unique face in the sense that it will be the lowest point of any closed face. Okay. So, for instance, if I look at this one is the lowest vertex of some face, this one will be lowest vertex of some face and this face better be bounded. So, this property only holds for bounded faces, right. So, if there are n choose 2 intersection points, there are definitely n choose 2 faces plus the unbounded faces, okay. And the unbounded faces also have a very nice structure. If you, I have drawn this diagram, if I could actually zoom out, then you would have, what would you have seen from very far? Suppose I zoom out on this, what happens? Okay, let me just maybe draw a diagram. So, if I zoom out, I claim that if I went very far, okay, it will basically look like something like a bunch of lines. Okay. Is this visible or this line? Okay. So, the entire interesting part of the arrangement, the bounded faces, will be limited within some maximum x coordinate, maximum y coordinate of the intersection points, right. So, it is all sort of just confined to a small region, okay, and there are these basically outgoing rays, right. So, there are basically these 2n rays going out, right. So, from far any arrangement would look like this, right. All the intersection points are confined within some region, okay, and there are basically lines going out and the good thing is that these lines can also be ordered, in some counterclockwise or clockwise manner. So, this is one way to think about arrangements, that when you go very far, all the intersection points are confined to some region. You can bound it by the maximum y coordinate, x coordinate of the intersection points, and the rays are kind of fanning out and they can be ordered. Right. So, then what happens if you go to the, so as I argued that every intersection point is the is uniquely sort of associated with a face, because it is a lowest point of face. Okay. So, there n choose 2 such faces, plus there are these faces which are unbounded faces. And how many faces are there? Unbounded faces? So, basically you go from, so all these are faces, right. Basically this is a face, this is a face, this is a face, and so on and so forth. So, about another, there are n lines. So, there are 2n rays, okay, is 2n. So, total number of faces to n choose 2 plus 2n. So, this is a geometric way of arguing rather than plugging it into the Euler's formula. Right. Any doubts? Okay. So, we have got a bound on the number of faces, number of vertices, number of edges, and they are all linearly related because it is a planar map finally. What else? So, okay. So, the other thing to notice about this diagram is, oh, by the way, let me also point out very quickly that in d dimensions, total number of vertices is how much? So, in 2 dimensions, 2 lines intersect in a point. Okay. In 3 dimensions, 3 planes will intersect in a point, right. And let us again assume the simplicity of the arrangement, that is, no 4 planes intersect in a point. So, I am saying the d dimensions total number of vertices, assuming no d plus 1 planes are concurrent. It just keeps our calculations easier, and it is also the worst case. Actually, if they are concurrent planes, there are fewer vertices. You can argue that. Right. So, so that will be what then? And choose d, right, and roughly about n to the power d. So, in d equal to 2, it is about n square, actually n square over 2. I am forgetting the constants basically. I am doing away the constants. So, it is n to the d. So, the total size of the arrangement A of, let us say, L is equal to number of faces plus number of edges plus number of vertices. If you think about it like a graph, okay, and this is basically O of n square. In the 2 dimensions, that is easily established. Now, in higher dimension, that is slightly harder, because in higher dimension you have to deal with many kinds of faces and facets actually. So, in d dimensions, you have various things, right. So, you have, let us say, facets of dimension, let us say I, and I is basically between d minus 1 to 0. So, 0 dimension is a point. A point is a d dimensional 0 dimensional geometric entity, okay, and d minus 1 dimensional is the actual plane, right. In 2 dimensions, the line is a 1 dimensional structure that is sitting in the 2 dimensions, and there is a point, right, and there are faces. So, actually I should plus, of course, the faces themselves, I should write, sorry, the faces themselves are d dimensions, because d dimensional faces. These faces are actually that encloses some volume, right. So, they are facets of lower dimension and there are these faces. Okay. Now, to get a bound on all this, the total size of the number of, I need to get a bound on every facet of dimension I. Okay. What is easily established is the number of vertices, the 0 dimensional facets, there are n to the power d. But now, I have to also work on the other kinds of facets, and that takes a while. So, I will skip this part here. Okay. It's actually not that hard, but on the other hand something laborious, right. Actually, from this assumption about simplicity, okay, you can figure out that a I dimensional facet is defined by exactly d minus I hyperplanes. So, when it comes to 2 dimensions, 2 lines define a point. Okay. So, there is an intersection basically. As you intersect more and more hyperplanes, the dimension is going to reduce by 1, right. That is where it comes. So, an I dimensional facet is defined by exactly d minus 1 I hyperplanes. And so, therefore, now you can actually write down this series of d choose d minus I summation, right. So, you will have to basically then do this. So, total number of I dimensional facets is d choose d minus I, which implies that summation over all I dimensional facets is summation of d choose. Oh, just a moment. I'm sorry. They are n, right. So, among n I choose d minus y. So, okay, it will be total facets of all dimensions summation. Right. So, if you work this out, again you will actually see that it will turn out to be about n to the power d roughly, but with a caveat that higher dimension is extremely difficult to visualize. Okay. And what we are going to suppress in this is that when I say it is going to be order of n to the power d, I am not looking at the constants, and the constants depend on d. Right. So, with that caveat, this is about order n to the power d. So, remember, whenever we are working in very high dimensions, okay, actually things grow very quickly with dimensions. Okay. It is called the curse of dimensionality. Okay. Again, we won't be able to discuss it in this lecture, but you will all often come across situations where you will see that number of facets basically are going to grow exponentially in dimensions. Okay. It is to some extent captured here, but not the full extent of it, and that is why we always talk about not very high dimensions. We call it fixed. We use this term called fixed dimensions. Okay. When we say fixed dimensions, so there is this. In geometric algorithms, we often use this notion of fixed dimension. So, fixed dimension essentially means that d is not scaling. Okay. So, when I write a formula, let us say that something like n to the power d, it may have a hidden constant to the extent of maybe even d factorial, which is d to the power d. But if you consider d to be fixed, that is, it is like a constant, it may be 10, it may be 15, it may be 20. then we actually using the big O notation, or let us say abusing the big O notation, we can completely do away with the d factorial, because you know that if it is constant, it is some number, very large number times n, okay, can be written as big O of n. But only if we consider d to be non-scalable, that it is fixed once and for all. But then if you look at the growth with respect to d, you cannot treat it like that. Then you have to look at d factorial as d to the power d. Okay. So often in many geometric algorithms, we say it is a fixed dimension, okay, and it's often confusing to people who have not read the literature. What does it really mean? It really basically means is that it's a relatively small dimension where you can ignore the leading constants. That's what it means. Okay. So even in the case of arrangements, in higher dimensions, n to the power d actually has a leading constant which is quite large, but we suppress it. Just say that it is big O of n to the power d. So this is basically about what is this structure, this arrangement structure that we have, whether it's in 2 dimension or d dimensions. This is the size of the structure, right? This is basically all sorts of facets and faces. Why is size important? Because finally, we may want to store it in a data structure, right? Eventually, what are we doing? We have a set of lines, okay, and if you want to create a data structure like what we started in the morning, that tell me, which, if given a query point, which line lies above it. Then I created those parallel slabs, right? Now each parallel slab basically had lines intersecting. How many slabs were there? There were n square slabs, right? Each slab had n lines, which means that the space of the data structure was n cube. Okay, let me just quickly show this. We never discussed it then. This structure, right? So each slab has size n, because there are n lines intersecting, and if you want to create a data structure, ordered data structure, size n. There are n square slabs, because these slabs are being defined by the intersection points. This is only in 2 dimensions. In 2 dimensions, we have, it is already n cube. In d dimensions, it's going to really grow. Like in fact, can you even guess how fast it grows? It's not n to the power d. This structure, if we generalize to higher dimensions, grows as n to the power 2 to the power d. It is a horrendous thing, so we will never actually do it. It's just that it gives you a very simple search data structure. Here I can do with 2 binary searches, in d dimensions I can do with d binary searches, but the data structure itself will be huge, okay, n to the power 2 to the power d. Okay, so let me just write it down, perhaps in 2 dimension search data structure has size n square. Well, actually, maybe I should write n choose 2 times n, that is about n cube. In d dimension, so this structure can be extended to d dimensions. Okay. So when you have these planes, okay, and you are going to look at the pairwise intersection of planes, that will be a line, and then the lines can be projected into the x z axis, and then you can define these vertical cylindrical kind of structures, and then within the cylindrical structure there will be no intersections. Okay. So this taking pairwise planes creates n choose 2 lines, then taking the pairwise lines, it creates n choose 2 choose 2, that is n to the power 4. So that's how it keeps growing basically. So if this structure were to be generalized to higher dimension, it grows at a horrendous rate, right? So in d dimension, this scheme requires n to the power 2 to the power d space. So query is very fast, it's d times log n, but space is horrendous. Right? So again, the upshot is that many things work well in lower dimensions that don't scale up very well in geometry, and that is one of the basic problems. And why are we interested in higher dimensional geometry? Well, not because I am trying to solve what I look at the real life problem, real life geometric problems. This room is a 3-dimensional structure. So, oh, it's a -1 maybe, so I am missing out something. Perhaps, so is d equal to 2, yeah, so it is a -1, sorry, thanks for reminding. So Does it work now? 2, 4. So it is 2 to the power d minus 1. It is not 2 to the power d minus 1, it is 2 to the power d minus 1, the whole thing. So then if you have d equal to 2, it is 2 to the power 2, 4 minus 1, 3 into the power 3. Right? Well, at that rate even minus 1 does not make any difference, but yeah, that is true. So, so things in real life that we try to capture using geometry, those are all like 3-dimensional structures. Okay? We grow in dimensions, or there is a requirement in dimensions when we try to model, basically all kinds of other problems using geometric methods. For instance, database problems. Database problems can be always recast as a geometric problem, and those problems become very high dimensional depending on basically number of attributes in the data structure. So if I have 10 attributes, we need to go to 10 dimensions. If we have 100 attributes, we need to go to 100 dimensions. Okay? So things like all kinds of database problems, clustering problems, these are not, we don't see the clusters in 3 dimensions in real life. These are clusters coming out of other kinds of input, which have many, many parameters. So when you actually map it to the geometry, it is mapped to very high dimensions, and then these kind of techniques becomes pretty much useless because they scale up very rapidly with dimension. So whatever we do in geometric algorithms, there is this caveat that low dimensions can be very misleading. Okay? High dimensions grow so rapidly that you will not be able to use these algorithms in real life. So the real geometric problems is okay because we are confined by our ability to only see or feel 3 dimensions. Whether God has made 100 dimensions, we don't know, we can't feel them, right? But other problems that are recast as a geometric problem, you may have issues. Okay. Fine. So let me go back to the arrangement part. So higher dimensional arrangements are pretty much useless because it grows as n to the power d. 2 dimensions is still fine. Okay. Now what else are we interested in an arrangement? Okay. Let's look at that. So okay, maybe I should redraw the diagram. Okay, just a minute. So let me again redraw some diagrams. I think I have drawn 5 lines, 1, 2, 3. So let me number them. L1, L2, L3, L4. Maybe I can draw one more. Maybe I should have drawn, I should have used 5 colors. Let me see. Let it be like this. Okay. Now, at any so I have this set of lines. Let me draw a vertical line at some point. So some fixed value of x, I draw this vertical line. Right. So if I don't have any vertical line in the arrangement, okay, I have no issue. So, as I said that let us assume that there is no vertical line in the given set of lines. So, when I draw a vertical line, there is nothing that it coincides with. So, it always cuts, it intersects. Right. So, if you have n lines, so if you have 5 lines, there will be basically 5 intersection points. Right. Oh, I have more than I am missing one line somewhere. I had not labeled it. 1, 2, 3, 4. No, I have 1, 2, 3, 5. Okay. So, I have these 5 intersection points. Now, this vertical line defines what is called basically the levels of arrangement. What do I mean by the levels? Okay. So, if I keep moving this line, okay, horizontally, okay, the intersection points will change, but at any fixed x axis there will be 5 intersections, unless I am at the intersection point. Right. Now, the part of this plane, this is the plane. Okay. So, the part of the plane that lies below k minus 1 lines, that is called the kth level. Okay. So, the subset of R square, the plane that is below k lines is called kth level of. So, this is the arrangement, right. So, of this arrangement I have defining what is called the kth level. Okay. Let us call it denote by a k of L. So, according to this definition, we can even have a 0 level, right. So, this part basically is the 0 level. Because it is below the first line. Okay. And I can draw the boundary of the 0 level easily by this, right. So, maybe I should do this. So, this is the boundary of the 0th level, right. And then as I cross this boundary of the 0 level, then I get the first level, level 1, right. And how is the first level going to be defined? Again, it is going to be between some boundaries. Let me now try to use another color. So, it comes here. Okay. So, this is 0 level, this is first level, and the first level should always stay above the 0 level. So, at this intersection point I must diverge, okay. Then I come here, and then I come here, and I come here, and I stay there. Okay. So, the entire portion below this dark yellow line, okay, is level 1. Then I can have second level, right, 2. So, then the second level will start from here. So, how do I start? I basically go to the extreme left, where basically there are no more further intersection points, and I start counting basically the lines, right. So, I start from here. I cannot go above, because if I go above, then I will be in level 3. So, I should follow at every intersection point, basically we have a break, right. Then again I go here, and then I sorry, I made a mistake. Should have stopped me. So, I go here because that is the yellow line. It is like the metro lines, right. Right. So, this is level 2, right, and then I will have maybe with a green, you get the idea now, right. I go here, I go here, I go here, go here, go here, level 3. So, I am using different colors for different levels, and then finally, I have level 4. Level 4 will start from here and kind of finishes here. So, you get the idea? All right. So, and the edges basically actually sorry, I should need to revise this. Sorry, the edges. So, edges basically means that it should be on one of the lines. So, the edges of R square that is below k lines is called the kth level. So, I have drawn the 0th level, 1 level, 2 level, and the subset of R square below the kth level is known as less than or equal to k level. So, let me see if level, sorry, less than or equal to k level denoted by A less than or equal to k of A. Okay. So, the portion that I showed in yellow actually is the less than or equal to 0 level, okay. But whatever I draw on the edges, those are exactly the kth level. So, the edges define the kth level, less than or equal to k is below that level. Okay. So, this actually takes care of all edges and all vertices, right. So, the arrangement takes care of the levels, basically union of all levels, union of all levels define A of L. Now, what are the properties of these levels? Why are we even defining or interested in the levels? That is the question. So, one thing that you may notice is the levels observation, the levels are monotonic chains, monotonic. So, monotone with respect to x. Right. So, when you follow a level from left to right, it will never bend backwards, it will always move forward, because it bent backward, obviously it is not a level, because if it bends backward, one of them is higher than the other. So, it cannot be. So, if you draw a vertical line through any of the levels, okay, it will intersect exactly at one point. So, you take any level and draw a vertical line, it will intersect exactly at one point. Okay. However, you can see that the level 0 and the level 4 has a special structure. Can you tell me what? Level 0, the bottommost level and the topmost level, they have a special structure. What is the structure? all the levels are unbounded, defined by lines, right? They are all extend to infinity. So, they are all unbounded in the sense. Oh, well, I see. Okay, what you mean? So, yeah, it's unbounded. That's one. Okay, fine. I get what you see. What else? What is the shape of those? Yeah, exactly. So, the topmost and the bottommost levels are convex. Okay. Well, strictly speaking, one is concave, one is convex, but let us use the term convex. Okay. So, this is observation 1, and observation 2 is the topmost bottommost chains. So, not only they are monotonic, but they are also convex. Right. So, these are some of the properties, the main properties that we get out of a level. No, not necessarily, not at all. In fact, you can see that they will be bent. Look at the red chain, it is bending in the other direction. So, it can bend in both directions. Okay. So, good point, not necessarily true. That's a good point. So, topmost and bottommost have this nice property, intermediate we do not have any property. They are monotonic, but not necessarily convex. Okay. Another thing that people are interested in. So, this monotonic chains, by the way, let me give you a quick example of this. So, we had done this. Let us go back to this transformation. Okay. And you recall that this diagram is basically the lifting transform. Right. We took those points, projected onto this paraboloid, okay, and you drew these tangential planes at those points. Okay. And I am sure you have discussed in your Warner diagram lecture that this is basically nothing but you look at basically a set of lines or set of planes, and this is the topmost level. So, the topmost level basically corresponds to the nearest neighbor Warner diagram. Right? Because if I project it to the plane, it exactly gives me the Warner diagram. Right? So, that topmost level, you construct the intersection of the topmost level and you just project it, it is the Warner diagram, because that corresponds to the nearest neighbor. You go to the next, because of this relation that the distance between 2 points is the square. So, this is related, right, the distance between the 2 points and the vertical distance, they are related by a square. So, the closest neighbor will be the closest when we shoot down a ray from this point, right, whichever is the closest. Now, there are other planes below this, right. So, there could be other planes, for instance, I could draw another plane. Okay. So, that the point corresponding to this plane, okay, is not as close as the point above this, right. But then again, from the same relation, you can say the next one must be the next closest. So, Warner diagram is not only about nearest points, but also about the second nearest point, the third nearest points, and the fourth nearest points, and so on and so forth, all the way to the furthest neighbor Warner diagram. So, when I basically do a ray shooting from this point, this is the projection. Sorry. So, this is B projected on this. This is like a a one dimensional Warner diagram, but it holds for 2 dimensions, 3 dimensions, whatever. So, from there, the closest point, the closest plane corresponds to the closest nearest neighbor, the second one the second neighbor, and so on and so forth. And therefore, the second one you can actually construct this level 2 of the arrangement, what I said was a level 2 of the arrangement. So, the topmost level gives you the nearest neighbor Voronoi diagram. The next level, again if you project it, will give you the second nearest neighbor, the third nearest neighbor, all the way to the bottommost layer will give you the furthest neighbor Voronoi diagram. And the furthest and the nearest are easiest to construct because they are convex. So, if I know how to intersect planes, that is construct the intersection of planes, then I can construct the nearest Voronoi diagram and the furthest Voronoi diagram. The other ones are harder to construct, but they are all related by this arrangements. So, once I have the arrangements of the projected lifted transform, okay. So, let me point this out. The arrangement is of, let us say, the duals of the points. Okay. This is the dual plane of P, okay, corresponds to the k nearest neighbor Voronoi. So, if P is the set of points, so I should not say dual, okay. Let me change that, let me call it D star, okay. Is it a D star of P is the lifted transformation. So, it is not the dual, it is not the point to line, it is basically lifted transformation where the planes are actually tangential to the paraboloid. So, I am saying basically, let me draw this diagram again. So, I am given these points and I have the unit paraboloid. So, this is your P, these are the lifted transform, the points projected to the paraboloid, and then what do? I actually draw the tangents, right. So, this is a tangent, this is a tangent, this is a tangent. So, there could be all kinds of tangents, right. So, in 2 to 3 dimensions these are planes, right. So, I am talking about these planes, the planes then this arrangement basically. So, the kth level of P corresponds to Voronoi k of P. So, again you have got something because of the dual transformation or lifting transformation. The lifting transformation and dual transformation are very related actually. Right. So, you have got you do not have to design Voronoi diagram algorithms separately. You can just construct the intersection of the half places, half planes, half spaces and get the Voronoi diagram out of it. So, it is again a 2 for 1 deal. Now, it is a 3 for 1 deal actually, right. So, because of the dual transform you can get these things. Okay. All right. Now, I just take another 5 minutes, okay. Sorry. So, my last topic for arrangement is the notion of what I call the, so I have defined levels, now let me define this thing called zone. So, So, I again have some lines right. So, again a set of given a set of lines. So, I have let us say a line that is not part of that. Okay. So, maybe I draw a line like this. So, it is not geometrically straight. Let me just correct it. So, this is the line that I have drawn, some line L, okay, and given lines L1, L2, Ln. Now, this line that I have just now drawn is going to intersect this arrangement, right. How many point of intersections are there? N points, right, n lines, n points. Okay. So, clearly these are the intersection points. Okay. So, it intersects all the lines. Now, what I want to do, I want to look at basically all these are also sometimes called cells, right. The faces are also sometimes called cells, or let us say faces. Okay. So, look at all the faces of the arrangement that it intersects. Okay. So, the face basically is this face, this face, this face, this face, this face, whatever it goes through, this face and so on and so forth. Okay. But this is not a face that it goes through, right. This is not a face that it intersects. So, only look at those faces that it intersects. Now, since it intersects n lines, okay, it intersects n faces, right. Now, what I am interested in is so consider all faces of that L intersects. This is called the zone. Okay. So, that is a zone. You can think about it like that this red line actually is illuminated. Okay. And all the lines are basically opaque. Now, if I illuminate this, look at the part of the arrangement that lights up. The light cannot pass through the lines. So, that basically is the zone of the arrangement. Now, the zone of the arrangement is what we are interested in are two things. One is that what questions what is the size of the zone in the worst case. So, size basically means the summation, okay, over all edges in the zone. Yeah, that is basically what it is. So, I can say that E intersects zone is not empty, right. So, I look at all the edges. So, if you look at the faces that the line passes through, so for instance, it has this is an edge, okay, this is another edge, this is another edge, this is another edge. So, the first face itself has 4 edges, right. The next face again has this, this and this. So, let me count an edge could be visible from either side. So, let me count it as 2. Okay. So, it is basically what I am looking for is the total number of edges summed over all the entire zone, summed over all faces that the line goes through. So, what is the size of that? Now, you can see that one face can be very large, right. I can have a situation where, I could have a situation where a single face in the zone can be size n. Do you believe this? So, basically it is like I look at the intersection of all the lines, and that intersection of all the lines can have size n, because I can make all the a situation like this, right. So, this is an arrangement, and if the line passes through this one, this face basically has all the possible edges. So, a single face can be very bad, it can have size n. Now, if I use that bound, then the size of the zone would be n times n, because no face can be more than n and there are n faces. So, that will give you n square. Okay. But let me give you a surprise, the size of the zone turns out to be order n, it is linear. Okay. So, that proof I will not be able to give now, maybe I will do it in the afternoon tutorial session. Okay. I will give you a proof of that. So, this is where I will end theorem. Zone L of arrangement of these L lines is order n. So, this is the surprising result. And why is the zone theorem useful? Use of zone theorem. There are many applications, but one is simply in, we have never discussed this, how to construct the arrangement. So, this figure that I have been drawing, okay, this planar graph, how do I even represent the planar graph? Do you know how to represent a planar graph? Have you ever done it anywhere, or was it discussed in any of the lectures? Okay, so that takes a little bit of effort, maybe I should have done that, but right now it is too late. So, let me just say that this to represent the planar graph, basically you have to show that every face, you have to represent every face. So, every face is basically defined by the edges, right, and the edges are basically defined by the two consecutive vertices, right. So, this is the structure that you basically have to store. Okay. And so, now to construct this, given that the size of the arrangement itself is n square, can you construct the arrangement in order n square time? Now, constructing the arrangement in, so I am saying that order n square log n is easy. Can you tell me why? If I had to construct this in order n square log n, it is very easy. It contains all the information, and what is that? All I need to do is take any line, compute the intersection points and sort them. So, on every line I have a sorted set of intersection points. Now, if I have that, then I can easily find out any face, right. So, if I have to trace out a face, let us say this one, I just start from here, this is the next intersection point, then I find in the next intersection point I must go backwards, this is the intersection point stored on this line, then again I trace it like this and I finally close it. So, I can easily trace a face or an edge given the sorted intersection points on any line. So, n square log n is very easy, because there are n intersection points on each line can be sorted in n log n time. So, it is n square log n. But then what you can do is, from this bound on the zone theorem, you can do it incrementally. So, when I add the next line, because the zone is only size n, okay, so zone can be constructed incrementally by adding the lines in any sequence and maintaining the data structure. This is absolutely my last line, and this takes time, basically order I. Okay. So, here you stop here, because every line I can add in order I time, because the zone is order I. So, to be a little careful about that. Next line, little bit more time, little bit more time. So, it is big O of I for adding the ith line. So, the summation is order n square. So, you can beat the n square log n bound using the zone theorem. Okay. And I will try to give you a proof of the zone theorem. I was hoping to do it, but it's time is too little. I will do it in the question. Every line in, say that again, every line in? Yeah, let me go back. Just a minute. What happened? So, can you tell me from here? So, so this L, every line can, oh no. Every line can, well, yes and no. So, yes and no. So, it is effectively some kind of an averaging argument can be used to show that every line can can contribute only a constant to the zone. So, when I do a proof in the afternoon, basically that is what I am going to do. I will show you basically that every phase can be split into two chains, and on each side of the chain a line can contribute only once. Yeah, that is a good point, but I am not sure it is strictly true. But it is something like that. Yeah, I won't vouch for it. Yes. But some lines may show up more often than others. So, I won't say that it is strictly true. I think you can construct a counter example where a line can show up many more times. Okay. All right. Thank you.